So in our next section, we're going to be focusing on what are the different failure scenarios that we could run into with a virtual port channel. And first we'll talk about what is the correct order that if the member port fails or the peer link fails or the keep alive fails, how does the system deal with that in order to continue forwarding traffic down to the destinations. Then we'll look at some of the problem cases that if you design the system wrong, depending on where you're placing the end hosts, if they're on the vPC primary versus the secondary, if we're doing only layer 2 switching versus layer 3 routing, what are the problems that we can run into? And then we'll talk about, from a design point of view, what are some of the workarounds for that we'll see most of the time they're not related directly to configuration. A lot of this has to do with the physical design, like the physical wiring of the system, and how much redundancy is built into the platform. Like, are we wiring the links between multiple line cards? Do we have multiple supervisors, multiple power supplies, and so on and so forth? Otherwise, we can end up in some strange cases where there's a failure and then the system is not able to recover from it. And the end result is you need to manually go in there, turn vPC off in order to get the system to fail back to underlying spanning tree. Okay, so first let's review what we talked about with the basic configuration and what's the order of operations that the vPC is supposed to initialize. Okay, so first off, the vPC process is going to start, so we're globally saying feature vPC and the vPC domain number. We know that that has to match between the vPC peers. We're then creating the vPC peer keep alive, which is going to be a UDP packet at port 3200. It's a unicast from the address that we define under the vPC domain, so it's basically just a ping back and forth between the neighbors. Then once the keep alive is established and we know that we have reachability, basically the boxes are alive, then we can form the peer link adjacency. Adjacency here meaning with the protocol Cisco Fabric Services over Ethernet, or CFSoE, and the system then starts to synchronize the control plane. Okay, along with this, the two peers are going to go through an election to determine who is the primary peer, who is the secondary peer. In a properly designed case, it should not matter who's the vPC primary, who's the vPC secondary. But we'll see in some of the problem cases today, it will make a difference depending on where the failure occurs, and then the secondary not being able to recover from the failure, or potentially the primary not being able to recover from the failure. And this is going to be due to a layer 1 design issue, essentially. Okay, so we form the election, then we're going to run our consistency checks. That's going to check the config of both of the boxes to make sure that the global parameters, like what type of spanning tree are we running, is matching. The interface parameters, like what are the different VLANs that we're routing. At the port level, are we doing something like spanning tree BPD filtering? Do we have one side configured as an edge port and the other side configured as a network port? Okay, assuming that we pass the consistency checks, then we're going to enable the layer 3 interfaces. Okay, so layer 3 SVIs, this is our interface VLAN 10, for example. Okay, VLAN 10 is one of the VLANs allowed on the peer link. So we start to advertise this assuming into our routing protocols, like we have the switches as the layer 3 gateways for the servers. And then finally, we're going to bring up the vPC member ports and start to forward traffic at layer 2. Now, from this order of operations, the system is specifically putting a dependency on the items here that the peer link cannot form unless the keep alive is formed, and then likewise the member ports cannot come up unless the peer link is up, and the member ports would not want to come up before the layer 3 routing is up. This is to make sure that if you start receiving traffic in from the servers at layer 2, but for some reason OSPF is broken, you don't want to receive traffic in that you're not able to route northbound to the WAN. So it's basically giving some time for your IGP or potentially BGP to converge before you start to receive traffic in from the servers. Now, the first one of these that we need to be aware of, some of the finer details, is going to be the vPC consistency check. Okay, we talked a little bit about this previously when we were looking at our basic examples, and what this is doing is basically when we synchronize the control plane between the peers, they're exchanging their config parameters and they're saying, does my config match up with yours? So assuming that we're starting from a blank config and we don't have anything configured other than the vPC domain number, the keep alive, the peer link, and then the match config for the members, we should see that all of the different types of consistency are going to be matching. Okay, so specifically, there are 3 types of consistency checks that the box is going to run. There's a type 1 global, a type 1 interface, and a type 2 check. Now, the main difference between them is that the type 1 checks would cause the VPC to fail if it is mismatched between the two peers. Okay, so these are basically catastrophic errors, like if I'm running multiple spanning tree and you're running rapid spanning tree, we can't do active-active forwarding together because we might not have the same view of the underlying topology. Or if you are running bridge assurance because the port down to your memory is a network port, and I have configured it as an edge port that's not running spanning tree, then we could run into a loop in the topology. Okay, that would be an example of an interface level mismatch. Where the type 2 mismatches don't stop the VPC from forwarding, but it generates a syslog message and it gives you a warning to say, hey, this might be some sort of problem in the data plane that the VPC system can't really predict what the impact is going to be. So for example, if you configure jumbo MTU on one of the peers and you leave the default MTU of 1500 on the other one, and we think about this from the data plane point of view, so let's say that we have server 1 that's dual homed to 5K1 and a 5K2. We have a channel from the server's point of view, so it's running a team, and on the team it has its IP address configured. Then between the 5Ks we have the peer link that is, and actually there's a question here, can I share the slides? I thought I posted them. Let me add them in here real quick before we keep going. It's advancedvpc.pdf. You should see it in the file share now. Okay, so we have the server dual home to the 5Ks. And let's assume in this case that we have the server configured for using jumbo frames. So let's say it's using an MTU of 9,000 bytes. Okay, in addition to this server, okay, it's using 9,000 bytes, and let's say it has the IP address of 10.0.0.1, and it's trying to reach another server. Okay, let's say this is server 1. It's trying to reach server 2, which has an address of 10.0.0.2. So these guys are on the same layer 3 subnet. They're on the same VLAN. Okay, and one of the 5Ks, let's say 5K1, is configured with the default MTU of 1,500 bytes. We have the second one configured with jumbo frames that's set for 9216, which is the maximum. Now, the problem we would run into is that assuming server 1 is talking to server 2 with jumbo frames, anything that hashes to the right of the network and goes to 5K2 would be able to be forwarded down to the destination, because on these interfaces, or basically on the backplane of the switch, this guy has the jumbo support. So it's saying, I'm using 9216, your frame size is 9,000. Okay, it's going to be within my range of what I can accept. But any packet that goes to the left, that goes over to 5K1, it's going to get dropped in the backplane as the traffic tries to enter. Now, from a real practical point of view, this is kind of a tricky problem to troubleshoot, because when you're doing layer 2 bridging, there's no device to generate an ICMP unreachable message to tell you that fragmentation was needed. So this means that path MTU discovery would not function between these two end hosts. They wouldn't realize that there's a mismatch in the MTU, and you'll see that the end result is slow performance, because if it's a TCP-based application, traffic going to the right is going to be properly sent, traffic to the left is going to be dropped, and then we're going to have to retransmit the traffic to the right, and then final end result is going to be very low throughput for the servers. But it's kind of strange, like if you ping the boxes, it's going to be fine. You'd have reachability. You wouldn't notice that type of issue unless you're actually testing at the application layer and you happen to be generating jumbo frames at the same time. So we'll see that when we look at the show VPC or the show VPC consistency parameters, it's going to give you a list of the switches side by side, and you basically need to go top down and look at each individual row, find where there's the mismatch, and then that's going to be the potential problem case that you would run into.